So we are live. Section 4.3, balancing chemical equations. This is tricky. It says this, if we blank two chemicals together, well, if we mix two chemicals together, a new chemical may be formed. Not always, but it may be formed. We have a fancy name for this, begins with the letter R. We call this a chemical what? Reaction. This is a chemical reaction. When you dropped calcium into water, one of the byproducts was hydrogen, because it blew up. This is the fun stuff. Some terminology. These are some of the vocabulary words that you're going to need to know for your test. Substances that react are called, does anyone remember from last year? It's kind of an easy word to remember. What do you call a substance that reacts? It begins with the syllable react. Yeah. Reactants. Yep. Substances that are produced are called, and this one's also kind of easy to remember because the word produced is sort of in the answer. Yeah, products. And now we come to one of the fundamental laws of science. This law was only proved about 300 or 400 years ago, which sounds like a long time. Actually, for a long time, they didn't think this was true. It says, you blank, you cannot create or destroy atoms. What does that mean? Therefore, the same number of atoms must be present before and after the reaction. The same number of atoms must be present before and after the reaction. And this is going to guide us for the next couple of days. We call this the law of conservation of mass. Thunder and lightning should go off right now. It's that important. The law of there should be a distant rumble of thunder in the background. The law of conservation of mass. Hugely important. We call it the law of conservation of mass. So, the law of conservation of mass.
If it's wet, don't put it in there.
It wouldn't be wet. The only reason it would be wet is that people were using it when I was out of the room. Right? Right. Conservation of mass. This is going to allow us, Ty, to predict ahead of time how a reaction will end up and what proportions the atoms will all rearrange and recombine and split. The number of atoms before has to equal the number of atoms afterwards. They don't magically vanish. Okay, that's a lie. For the longest time, they thought they didn't magically vanish. And then Albert Einstein came along and he showed that if you split an atom, some of the matter is actually transformed directly into energy and you get a huge explosion. So I guess what I should really say here is the law of conservation of mass, as long as we don't go nuclear. Okay? Are we going nuclear? Not for a while. So here's a standard reaction equation. You have coefficients, just like in math. Those are the numbers in front. You have your reactants, and you have your products. Is this a balanced equation? Well, let's see. How many hydrogens are there on the left-hand side? Well, there's 2 right here, but what number is in front? A 2. How many hydrogens are there on the left-hand side, grand total? 4. How many hydrogens are there on the right-hand side, grand total? 4. That part checks. How many oxygens are there on the left-hand side, grand total? How many oxygens are there on the right-hand side, grand total? Careful. Not 1. What's in front of this molecule right there? A 2. How many oxygens are there? 2. This equation is balanced. By the way, why do they have an O2 right there? Why not just an O? Remember, we called these diatomic atoms. When they're by themselves, they always appear in pairs. And you may recall I gave you the name Hofbrinkel, which stands for hydrogen, oxygen, fluoride, fluorine, bromine, iodine, nitrogen, and chlorine. All of those always appear in pairs, and I'll show you an easy way you can spot them on the periodic table too. But not right now. Here's what we're going to be doing. Chemical equations are used to represent chemical reactions. In fact, an equation tells us what reacted, what was produced, and how much of each. If you take 2 hydrogen molecules, a total of 4 hydrogen atoms, but hydrogen likes to pair up into a molecule. If you take 2 hydrogen molecules and you combine it with 1 oxygen molecule, you will get 2 molecules of water, of H2O. We can use words, but that's a lot of writing. We usually use formulas to describe the reaction. Here's a formula. 2NO little g plus O2 little g, arrow, 2NO2 little g. Well, we have to translate this. That there means 2. Don't put an arrow there. I'm going to mark this up like crazy, so don't worry about copying this part down. What's the letter N stand for? Nitrogen. What's the letter O stand for? Okay. What would we call this? First of all, NO, don't write this down. Is it covalent or ionic? This is a good review for your quiz. How do I know, Amy? You're right. They're both on the right-hand side. Okay. What's the charge on what's the charge on nitrogen from your periodic table? 3 negative. What's the charge on oxygen? 2. So we should have a crisscross. Have they bothered crisscrossing here? They're not balancing the equation yet. They're just telling you what was at the party. They're not telling you how many of each person was at the party. We would read this particular sentence as follows. We would say, so 2 molecules of nitrogen monoxide, nitrogen and 1 oxygen is nitrogen monoxide, reacted with 1 molecule of oxygen. When you're done, can you just put it face down in the proper block? Thanks, kiddo. To form, how many molecules were formed afterwards? How many molecules were formed afterwards? Say it louder, you're right.
2.
Which 2? Yeah, this 2 right here. Okay? To form 2 molecules of, thank you, phone's in the desk drawer. What do I call, how would I describe NO2? I don't say nitrogen oxide 2. We use prefixes. Huh? Nitrogen dioxide. This is tricky, I know. I'm going to go slow on purpose, make sure we get the hang of this. So the coefficients, the numbers in front, the 2 right there and the 2 right there, they tell us which one where? 2 molecules of nitrogen monoxide reacted with 1 molecule of oxygen to form 2 molecules of nitrogen dioxide. Yeah, my handwriting is messy. Oh, how twice? Good point. Coefficients tell us how many molecules are involved. What do you think? What do you think? Make it a little bigger so you can read. Too big because you can't fit it on the screen, Mr. Dewick. How about that? That works. What do you think this little G here in brackets means? It's a good guess. Okay? What we're going to start doing this year is we're going to start to add the state of the atom. G tells you that the atom was a gas in a gaseous state. What do you think L stands for? Liquid. What do you think S stands for? Solid. And then this may be a new one. Does anybody know what AQ stands for? Okay. It stands for aqueous or aqueous, which is a fancy word for dissolved in something else, usually water. Okay. I wrote down here, reading check, page 205, reading check, page 207. Can you open your textbooks, please, to page 205? Sorry for those of you watching this at home. I forgot to turn the recording back on. The balanced equation. This tells us how many of each molecule. Come on, pen. React or are formed. And we always write this one in lowest terms if we can, looking at the coefficients. Sounds confusing. We're going to practice this. Next page over. Here's an example. Here's a word equation. Potassium reacts with oxygen to form potassium oxide. Here's the skeleton equation. Potassium. So here's my skeleton equation. Potassium. Hey, potassium is that one. Reacts with oxygen. Oxygen is that one. 2 oxygens because oxygen is diatomic. To form potassium oxide, that one there. Miller, why didn't they say dipotassium oxide? There's 2 potassiums, Why didn't they say dipotassium oxide? That's a tough trick question. We see? Yep. No. I'm being really sneaky right now. Yeah. Oh, it's ionic. It's ionic, isn't it? Potassium is a metal, yes? So for ionic, we didn't worry about the di, mono, tetra stuff. Ionic, it was just, if it's multivalent, use Roman numerals. Potassium isn't. Otherwise, ionics, we're just kind of reading it out. Still the IDE rule. Let's get the balanced equation. Going to rewrite it over here. K plus O2 becomes K2O. Now, some of you may reach the point where you can kind of just, Jessica, see the answer, and that's great. But if you want a systematic way to get here, until you get good, here's what I do. Once I've written down the skeleton equation, I'm going to try and balance this. I list how many of each atom there is on each side. How many K's are there on the left-hand side? One. How many K's are there on the right-hand side? That right now tells me this is not balanced. How many O's are there on the left-hand side? 2. How many O's are there on the right-hand side? I start out noticing, hey, it's not balanced. And then what I'm going to do is I'm going to add coefficients to see if I can balance it. I always start out with something that is not balanced. Now, both K and O aren't balanced. I'll start with the K's. How many K's do I have over on this side? How many do I have here? So maybe I can say, maybe I need 2 of those. How many K's do I have now? 2. Are my K's now balanced? Check. Let's move down to the O's. How many O's do I have on the left? How many O's do I have on the right? Well, maybe I can put a 2 there. Now that would give me 2 oxygens. Are my oxygens now balanced? Yeah. Are my K's now balanced? How many K's do I now have on the right-hand side? No longer 2. What? I heard 3, I heard 4. Which one? 4? Okay. How can I get 4 K's over on the left-hand side? How many K's do I have right now? Yes? No? How many K's do I have on the left? 4. How many K's do I have, potassiums do I have on the right? 4. The law of conservation of mass has been satisfied. How many O's do I have on the left? 2. How many O's do I have on the right? The law of conservation of mass has been satisfied. Is my equation balanced? This equation is balanced. So, if you're looking in your notes, let's see here, how would I write this down? Start with the bigger molecule, the K2O. And then the smaller molecule. So we started with the K's first. You need to put a 2 in front of the K2O to balance the number of oxygens. Put a 4 in front of the K to balance the number of potassiums. Pause, don't write pause here. I'm just going to write that. We're going to pause here. Give me 1 second.